In Module 5, our study of molecular thermodynamics is going to turn to a new type of system, that is, a system that contains more than one component, and how those mixtures of components alter some of those thermodynamic properties. I want to spend a few minutes just acquainting you with some of the differences of this subject so that we can distinguish it from our earlier study of one component systems and establish some ideas and some notation that I hope you'll find useful as you go through this module. First of all, when we have a multi-component system, and let me just put a little bit of this down in writing, a multi-component system, we're interested in more than just the usual thermodynamic quantities or properties. So for example, we usually have been looking at pressure, volume, temperature, and we've looked at number of moles, but only as a means of quantifying how much of the system we have. That number of moles now is going to shift to looking at the number of moles of each quantity, or I'll say the composition of our system. All right, so how would we quantify composition? All right, there are several ways we can do this. We can do it, one, by listing the number of moles of each substance. So listing number of moles, number. So that could be, for example, N1, N2, and so forth, for however many components we might have in the system. I'm going to use generally the index J to indicate that. So J is an index for the components. Okay, besides the number of moles, we could also specify a composition by listing the mole fractions. And this, in fact, is a very handy way of doing that so that we can then scale a system by a total size. But for any subset of that system, the mole fractions should be an adequate description. And we'll usually use X sub J. Now this is different. In the past I've used chi, the Greek letter chi, to indicate mole fraction. That's a common usage. But we're going to want to distinguish between mole fractions that are in liquid or solution. So I'll use X for that, from mole fractions that might be in the gas phase. And so I'll use Y to indicate those mole fractions that are in the gas phase. Okay, that way we can always tell the difference. And in particular, when we're dealing with a system that can be both in the liquid phase and the gas phase at once, that is, it's in a phase equilibrium, this will allow us to distinguish between those particles that are in each of those phases. A third way that we might do this if we just had a gas phase system would be, for example, partial pressures. All right, and those we might denote by something like P sub J, where again J indicates the component and P sub J is its partial pressure. So it would in fact usually be identifiable as the mole fraction, and I probably should use Y in this case since we're talking about gas, the mole fraction times the total pressure of the system. So another way of saying this is that the mole fraction in the gas phase is just the partial pressure of a component divided by the total pressure. All right, so these are different ways that we're going to be able to specify the composition of a system. Now, another distinction that I want to make is a distinction for ideal systems. Okay, and I'll just say that the word ideal is going to mean slightly different things depending on what phase our system is in. All right, so for example, for gases, I know that an ideal gas is one that has no intermolecular forces. That is, there's nothing, no attractive forces between molecules, nothing that causes them to behave other than just point particles bouncing around and bouncing off each other. It also means that those particles have no volume. Okay, and we saw that, in fact, when we went to non-ideal gases, we had to correct for both of these in the previous module. So hopefully not a surprise that ideal gases have this particular, these particular qualities. What about solutions? Well, I want to make a remark. Usually when we talk about solutions, we talk about liquids, liquid solutions. We can also have solid solutions. We can also have gaseous solutions, but we are primarily going to be talking about liquid solutions. If those liquid solutions are defined in the same way as an ideal gas, with no intermolecular forces, well, there's nothing that would hold those molecules together. They wouldn't stay in the liquid very long. They would all disperse as a gas. So in fact, we cannot say that an ideal solution has no intermolecular forces. Instead, we say that it has the same intermolecular forces between any pair of particles. All right, so in other words, this makes the distinction between a pure substance and a substance that's involved in a solution somewhat reduced. All right, so what I mean by same is if I've got two substances, A and B, the intermolecular forces between A and between B and B are essentially the same, and they're also equal to the forces between A and B. All right, so all of these forces are going to be roughly equivalent in an ideal solution. All right, what this means is that as we look at ideal solutions, our focus is going to be on the relative populations of the components. In other words, we're not going to have to focus on the forces between them because those forces are all identical. And so what that means is when we look at different properties, we're going to really be focusing on these relative populations. So in other words, everything is going to depend on mole fractions xj in the solution phase and yj in the gas phase. All right, now I want to shift page here so that we can talk about some other issues. The next topic that is a little bit different for these things are going to be phase changes and equilibria. And we're going to be talking a lot about phase changes, particularly evaporation, in this module. Now, what is the chief difference? Okay, well, first of all, I should say phase changes give us a window into the thermodynamics of systems. We've seen that in Module 4 as, the free energy, the Gibbs energy rather, basically determined everything in terms of the positions of the phase equilibria. And the same will be true when we talk about solutions. So we'll still want to focus on the Gibbs energy or on its molar counterpart, the chemical potential. All right, so what we're going to be doing is applying the principles that we've learned in Module 4. So I'll say applying Module 4 to more complicated systems, and in particular more complicated because they have multiple components. All right, what's a good representation of how this works? Well, remember in Module 4 we introduced the concept of the phase diagram. Let me draw just a poor man's version of the phase diagram. It was basically a plot of pressure versus temperature, and it showed us a map of where the different phases exist. And they typically look something like this. Go up to critical point, and we had solid, liquid, and gas or vapor on these phase diagrams. Okay, and for a single component system, it's a fairly simple map that we can make, okay, but an important map. What happens when we have more than one component? Well, now, in fact, we're going to have another dimension on this phase diagram, and I'm going to draw it like this. And this extra dimension, if you will, is going to be the mole fraction of one of those components. In other words, the composition of the system, the multi-component system that we have, is going to add another layer of complexity or another dimension to this. So I'm going to essentially make a box out of this and indicate that this mole fraction is basically going to go from 0 to 1. So it basically takes us from one plane here that represents pure substance 1 or pure component 1 to another plane, and I'm going to change color to draw the contrast, to another plane, and I'll, let's really fill in the plane here. This plane represents pure component 2. So those are the limits on this phase diagram that I have, so it's a little bit of a finite phase diagram. But what are we going to see? In pure component 2, I'm going to see a very similar sort of trace up to a triple point, up to a critical point, and up here. And I hope you're reading the red as being on a plane that's closer to you than the blue in the back that is on a plane farther from you. All right, so we're going to see similar sorts of traces for pure component 1 and 2. Of course, they will have different triple points. They will have different critical points. What about in between the two? What are we going to see there? Well, that's part of what we're going to examine in this module. So, for example, we could cut slices through this. If I sort of fill in the cube, as it were, I fill this in, we could cut slices that are basically parallel to the two end plates. And what that would do would be to capture at a constant mole fraction. What does this look like for a pressure versus temperature diagram? Okay, we could also cut it halfway this way, and that would be for a variety of mole fractions. We would be looking at, say, in this case, temperature versus mole fraction. Temperature is the horizontal distance, mole fraction is this distance. So we would be looking at a slice through this three-dimensional phase diagram that shows us that. All right, we can also draw a slice that cuts the phase diagram this way, and that will give us pressure versus mole fraction. So pressure is the vertical axis, mole fraction is this sticking out of the board axis. So I've made a real mess of this picture, but you get the idea that what we're going to look at is cross sections of a much more complicated phase diagram. So I'll call it a three-dimensional phase diagram whenever we have more than one component. And that's the only way that we'll be able to get a handle on what is actually going on with the phase changes in a solution. Now, I realize this may sound hopelessly complicated, but you'll see that these cross sections are actually reasonably easy to understand. I hope you'll find that way. And we'll be able to get a lot of meaning out of looking at those as we create them. And much as I'm tempted to, I will never show you the three-dimensional version of these phase diagrams because they're a little interesting. It's a little bit of a mind twist to take a look at them. Now, the last thing I want to talk about is notation. Okay, there's a few things that I'm going to introduce in the notation that you need to be aware of. One, the asterisk, whenever you see this as a superscript on a substance, it is referring to a pure substance. So this helps distinguish us from talking about properties of the mixture, which contains more than one substance, from a property that is of the pure substance. And I'll probably be reminding you of that as we go through. Another notation that you may see is that sometimes I may refer to N with a little squiggle under it. This is just my fancy way of writing the set of moles for each of the components of a mixture. All right, so you can think of this as being many different mole numbers, but rather than write out all those mole numbers, I'm just saving time by writing this as though it were a vector or something like that. All right, I also want to distinguish something else, and that is something that we learned about a little bit in the previous module. We identified the molar Gibbs energy as simply the Gibbs energy of 1 mole of the substance, and this was something that we identified with the chemical potential. We also identified the molar volume as something that was just the volume of 1 mole of a pure substance. All right, when we get into mixtures, these definitions change a little bit, and I want you to be aware of that and conscious of it. And in fact, we're going to call these things partial molar volumes. We're going to learn about that in this first lesson here. I say partial molar quantities, not partial molar volumes. And I want you to be alert to the difference in the way they're defined. Okay, when we defined chemical potential, one of the ways that we denoted it was to say that mu was equal to dg, the number of moles, with constant temperature and pressure. Now, in the case of multi-components, we're going to specify that the chemical potential refers to a particular component and that the partial derivative is done with respect to the moles of that component with all of the others held constant. All right, so there's some subtle differences there, and we'll talk about those as we talk about partial molar quantities. So I hope this has given you a good feel for what to expect in this module, and that it will help you understand some of the lessons that you'll see in the upcoming text segments and videos.